like an, you've got probably, if you submitted a paper this brief as college classroom, the professor would, correct your grammar a lot, but would generally understand what you were saying and think, yes, this student at least understood the comment. 7, that would be more like the English is getting really hard to understand, or the level of understanding of the problem. It's really hard to understand. It's hard for me to tell if you understand the question, because I'm trying to read it as synthetically as I can, but if it gets hard enough, then it's just hard to tell what you're trying to say. If it's a 6, so if you get an 8, a 9, or a 10, these are all good. 8, 9, and 10 are good grades. You're doing good. And you can get, if you need a B or above a B minus, you can get above a B minus if you got an 8 on this assignment and you keep working hard. But if you got a 7, you have some work to do. You have some work to do. You can still do well, but you either have some trouble expressing yourself in English that's pretty serious. It wasn't clear to me that you understood the problem or the solution. If you got a 6 or below, you're maybe not prepared for this course. If you got a 6 or below, it could be just you didn't understand what kind of paper I wanted you to write. So suppose you got a 6 and you said, I just didn't know you wanted me to answer the question. I thought you wanted me to just talk about my impressions about it, but next time I'll answer the question. Then, okay. But if you just said, well, no, this was my best effort, and you got a 6 or below, really think carefully about whether this is you got an 8, 9, or a 10, you're doing well. And you could easily get a B minus. And with a little work, you can get a B, a B plus, maybe an A. Well within that range. 7 is in the middle. There's something wrong here. It's either very hard to read or not clear you understood the problem I was asking you to write about, or both. But I think there's a chance if you work hard, you can get up into this area. But if you got an 8, 9, or 10, just keep doing what you're doing well. And I noticed that people who came to office hours often did especially well, because they can ask me and I can discuss with them how to question and what some good things to think about. So 8, 9, and 10, just keep doing what you are doing. You're doing good. 6 or below, think really carefully about whether this is the right course for you. 7, it may or may not be the right course for you. If you're willing to work hard, I can help you get better. But if you're in the 7 range, you need work because the English is hard to understand. And what I'm trying to really prepare you for is, if you, say, try to publish a paper in an English language journal, or give a paper at a conference in England or Australia or the United States, or if you wanted to just take a part in international scholarly discussion with somebody from India or something like that, would your English be good enough that they could generally understand you and see that you were philosophically engaging the problem, understanding the philosophical issue? In the 7 range, you're on the border. You need to work a little harder, but so if you're willing to work harder, I'll work harder with you. If you're not willing to work harder, well, you can keep getting 7s. I mean, that's what they do. 6 or below, there's problems, and I tried to be clear in my comments about what the problems were. So the grading is based on a combination of, and especially between 8, 9, and 10, a lot of it is 8, 9, or 10. Sometimes it's a little awkward, but I understand what you're saying. It's just a question of, was there something that I was like, wow, this, like a few people was really, really The English was just really, really good, and the philosophical insight was very good, where I said, wow, that's really good philosophical analysis. Then it's like a 10 or maybe a 9. 8 it's very solid. It's like, I understand the English, you made a good point, you're doing good. Plenty of potential to get even better. 7, like I say, these are the words. So I guess I'm repeating myself a little bit.
我还有没有其他问题？博士是吧？你们说话不清楚啊！你说清楚一点，忙呢，马上就要当老师的人。声音大一点，就是说啊。我的意思是说，人家的那个分数嘛，就是说最后的这个小的时候，就是加起来的分数可能全部嘛就已经，就是说在毕业以下，可以那时候再找这个问题涉及2个层面。第一是一个技术问题，是吧？可不可以转，对不对？第二是吧？第二是一个涉及这个可以说道德或者说素质问题，是吧？然后我就是熬到最后，我看到底能不能理解，是吧？关于技术问题，这个我大致知道答案，但是我希望你还是去问爷爷，问这个教学秘书，可以去问一下，我大致知道答案，但我希望你去跟他确认一下。关于这个，你应不应该这么做，我提2点。第一点，大家如果看自己的作业的话 ，Bryan 这个给你们改得很认真很认真，对不对？基本上每一篇作业估计要花很久时间。这个当时我们请这个 Bryan 过来的时候，他作为这个国际一线的学者，是吧？我当时没有想让他作为一个小学或者初中英语老师来改他的作业，是吧？纯粹浪费一颗智慧的大脑，是不是？浪费，这就像你请，是吧？我们的郭启勇教授，对不对？给你改一篇论文，这论文上充满了语法断句错误一样，对不对？所以我讲从这个道德或者从这个规范性的角度讲，如果我们这里有些同学我看到这个 Bryan Post 的这个 QQ 群上这个，就是对大家作业的几点建议，是吧？有些同学是直接百度或者是用翻译软件翻译的，对不对？我想这个从道德角度讲，这也是一个非常不道德的事情，是吧？这国际一线学者来看百度，是吧？翻译的这些东西，然后给你一字一字改，对不对？是不是？这也不能体现，不仅说不能体现我们大哲学系一个哲学博士的素养，是吧？这甚至不能体现一个人的素养，对不对？我这说的稍微严重一点，就是我觉得这基本，是吧？这是一个很不道德的事情，是吧？这个回到你刚刚说的问题，你说，比如说，我每次就百度，是吧？我看你忍不忍心每次给我5分或者6分，对不对？我就等到最后看怎么样，然后实在不行我就drop，是吧？我想这个是吧？好像没有太浪费你的时间，但是浪费了Bryan的时间，是吧？所以我建议是这样的：如果你觉得我非常想，是吧，提高我的英语成绩，然后呢，我觉得我还是有很大空间的，然后呢，我也很愿意花时间在这上面，你可以这么做，是吧？比如说你每次大概7分8分左右，是吧？你觉得这也是你自己用功来写的，是吧？可能有一些语法上的错误之类的，但是我觉得语法上你也可以找别人先读一读，是吧？找你的同学给你读一读再教，是吧？不要，是吧？用这个吃完饭时间5分钟，是吧？写一篇，是吧？交上来。就是如果你每次只是第一次作业嘛，可能很多同学还不习惯于这个美国研究生这个教学这个改作业这个过程，可能觉得像中国老师一样，是吧？瞄一眼，是吧？你花了5分钟写，他花了半分钟改，是吧？现在不是这样，你花5分钟写，别人花50分钟改，是不是？浪费国际一线学者的时间所以就是说，如果属于我刚刚说的情况，你还是不是用百度翻的，是吧？你自己写的，认真思考的你觉得还是想提高你的英语，想看看他的 comment， 是吧？你可以这么做。但如果你每次都是百度的，是吧？我觉得没必要，只是实在有损我武大哲学院的声誉，是吧？搞得回去 Bryan 在餐桌上说，是吧？武大的学生非常的有意思是吧？老是考验我百度翻译的怎么样，是吧？ 好吧？还没吃大米。No.
Sorry. I just, what you're saying was making me think of, there's a famous quotation, it's from the ancient world. I wish I remembered, if you remember which philosopher said it, but there was someone like Euclid or Pythagoras, but it wasn't. I don't think Euclid or Pythagoras. Some famous mathematician was talking to a king, and the mathematician was explaining to the king some of the mathematics that the mathematician was studying. And the king said, "This is really hard. Could you just give me the simple version?" And the mathematician said, "There is no royal road to knowledge." There is no royal road to knowledge. What does that mean? It means even if you're a king, there's no easy way to get knowledge. So the king was saying, yeah, this is good, but, I want the easy way to get knowledge. And it's like, well, there isn't one. If you want the knowledge, it's tricky. So it's, I know it's hard, and, and I'm sympathetic, and I also know it's especially challenging if your background in philosophy isn't especially strong. But there's no easy way, as Professor Lee was explaining, if you use something like, I think there were at least one paper I really thought this must be Baidu Translate because it didn't make any sense in English. It looked like the kind of if you took Baidu Translate, put Chinese in, and tried to get English on the other side, it's going to be a mess. I know because, sometimes I'll do that. I'll be like, how do you say this in Chinese? I forget. And I type it in the other direction. And sometimes I'm like, well, I know that's not it because I know that doesn't mean anything in Chinese, So I've tried it the other direction, not for a whole article, but I tried for phrases. And sometimes, well, this work. So if it doesn't work for phrases, it won't work for a whole essay. So, but again, as I tell my students in the U.S., 8, 9, 10, these are all good. It's just a matter of 8, 9, and 10. It's is it like a 10 would probably be even smoother English, very, very smooth English, plus really good philosophical insight. 8 is perfectly comprehensible English and good insight. Not amazing, but you understand the problem. You understand what the issue. That's really good. You should be proud of yourself. That's really good. Let's start talking about Kuhn. Oh, I'm sorry. And of course, Guoqingjie is coming up. I hope everybody has a great holiday. So our class will not meet next Tuesday. And since the class won't meet, I won't have my usual office hours on Monday. I'd have them if I thought people would be on campus, but I'm guessing most people will be traveling or doing things. So I won't have my regular office hours next Monday, and this class will not meet next Tuesday. But then we'll have a makeup October 11th, which is a Saturday, at this same time. That's the university does it that way. So the university said, this class doesn't meet on the 7th, but to make up for it, it does meet on the 11th, same room, same time. Then, that's on October 11th is a Saturday, then October 13th to 14th, that's a Monday to Tuesday, office hours and class schedule back to normal. We're just back to the way we usually are. So, no problem. So, let's talk a little bit about Kuhn. I had you read a couple of things for today. One of them is part of the preface to Kuhn's collection of essays, The Essential Tension. And one of the things he says there is going to prove especially important for the course in the long run. But to understand it, you need a little bit of background. And it's an interesting background. Kuhn was trained as a physicist, and he was planning on being a physicist and he completed almost all the requirements for being a physicist. But then, as part of his training, someone said, well, we'd like to teach a course, and the course we'd like to teach is on the history of science. You're a physicist, so surely you can teach a course on history. So he agreed. And so he did a little reading about what earlier physicists had thought about the world. And he found that when he read Aristotle, who's in many ways the father of physics in the West, there are, of course, earlier philosophers who are interested in the physical world, but in terms of historical influence, Aristotle is the father of Western physics. So when Kuhn first read Aristotle, he said, Aristotle seems really stupid. Aristotle's views seem absolutely absurd. But the more he thought about it, this puzzled Kuhn. Kuhn thought this was strange. Why did he think it was strange? Because, fortunately, Kuhn knew enough about Aristotle to know that when Aristotle talked about other topics besides physics, he was often deeply insightful. Aristotle is deeply insightful about politics. He's deeply insightful about issues in metaphysics. On many, many topics, Aristotle seems very smart. How is Aristotle so smart in all these areas and so stupid when it comes to physics? And another thing that Kuhn thought about was he said, suppose Aristotle is just stupid when it comes to physics. Why did so many smart people believe Aristotle for so long? So if Aristotle really is stupid, Aristotle really believes absurd things about physics, why did smart people believe him for so many years? So Kuhn kept thinking and reading and reading and thinking, and he describes it very movingly. He says, actually, let me read the phrase. I love this phrase. It's one of those nice phrases. It's so short, but it just makes you feel like you're there. It's very... One memorable and very hot summer day, those perplexities suddenly vanished. One memorable and very hot summer day, those perplexities suddenly vanished. What do perplexities mean? Perplexities is just a word for when you're perplexed, you don't understand something, or you're confused about it. So I'm perplexed as to why Aristotle says so many strange things about physics. I'm perplexed as to why people believed Aristotle for so long when his views are so absurd. And he said the perplexities vanished one hot day. I can just imagine Kuhn sitting in his office. It's hot. He doesn't have an air conditioner. It's a fan, maybe, and it's sweat coming down. He's like, I don't get it. And then he said, he got it. What did he get? He understood that for Aristotle is primarily a biologist. And as a biologist, what Aristotle's interested in is... What Aristotle's primarily interested in qualitative change in general, changes in quality of things, and for things in general, not just some things, but for all kinds of things. Like what? Well, a baby becoming an adult. That's a qualitative change. The baby has one set of qualities, the adult has a different set. And so Aristotle wants an account of how things change in their qualities. And he wants it to be a general account. He wants it to apply to everything. So on this view, motion is just a particular kind of change in quality. And it's really not a very interesting kind of change in quality either. For Aristotle, so this is Aristotle. Then for Galileo and Newton, they're interested in is quantitative change motion. This qualitative for Aristotle versus quantitative. In other words, what you can measure with numbers for Galileo and Newton. And in the case of Aristotle, he's concerned with qualitative change in general, in all kinds of cases. In the case of Galileo and Newton, they're interested in quantitative change, numerical changes, changes you can measure with numbers in motion. Not just any kind of change, like baby to adult, except insofar as you can measure how much a baby changes in weight to an adult. That's not really what Galileo and Newton care about. What they're interested in is quantitative change in motion. And Kuhn says once he understood that, all of a sudden the weird things, the seemingly absurd things that Aristotle said suddenly made sense. He said, yeah, it all makes sense. It's all part of his theory of qualitative change of things. But, he said, because I, Kuhn, was raised in the post-Newtonian world, when I do physics, I look for quantitative change in motion. So when I read Aristotle, he seemed absurd, because I couldn't figure out what he was doing. One way of phrasing that is we could say that... Hello? That Aristotle's paradigm, that's a word we're going to look at more, Aristotle's paradigm for how you do physics, his model for how you do physics, his view of how you do physics, is you're looking for qualitative change in general, whether it's biology, it's an animal, a caterpillar becoming a butterfly, a baby becoming an adult, the moon going around the earth. They're all examples of the same kind of qualitative change, change in qualities. The Galileo-Newton paradigm says, no, what we're looking for is changes in motion that we can quantify. So they're different paradigms. So at that moment, Kuhn had his first insight into what he would later call paradigm change. And he said that he learned a lesson that he tries to teach all of his students. And it's a lesson, since Kuhn is now dead, that I will try to pass on to you. He can't pass on to you, so I'll try to... I'm not anywhere near as smart as Kuhn, but someone has to do it, so I'll pass on this lesson. Kuhn said, when reading the works of an important thinker, look first for the apparent absurdities in the text. Ask yourself how a sensible person could have written them. He said, as a historian, when you're reading the works of an important thinker, don't ignore the parts that seem absurd. Focus on those and ask yourself, how could a sensible person, a rational person, an intelligent person have said those things? And then he goes on to say, when you find an answer, when those passages make sense, then you may find that more central passages, ones you previously thought you understood, have changed their meaning. In other words, by looking at the apparently absurd passages and thinking about why would a sensible person say these, you realize, oh, this is why a sensible person would say these things that seem. Then when you go back and look at other passages, even ones you thought you understood, their meaning will seem different. You'll see them in a new way. You'll think, that is really what he means here. I didn't understand before, but now I see what he did. So this is a good example of how we do history when we're doing it well. So Kuhn is telling us a little bit about how we came to understand a paradigm. We're going to talk some more about a paradigm. But in order to understand why paradigms are so important, it helps to understand the view of science that Kuhn is rejecting. The view of science that Kuhn is rejecting. There are actually several different views of science. But one of the simplest models of science, one of the simplest views of science that you could see Kuhn as rejecting would be the covering law model of science. The covering law model of science. Covering law. So how does the covering law model work? Well, I don't know if you can see it here, but at the bottom here I've written some blocks, some little blocks. What do these blocks stand for? I'm going to write a little bit. I'm going to draw a little bit. When I'm finished drawing, I'm going to switch boards so you can copy it or take a picture. First, I'll draw a little bit. So I've written some blocks. What do these blocks stand for? Well, suppose, and this is a very simple example. Suppose the first block on the left here is the observation that this chicken, chicken number 1, lays eggs. Shut up. So this chicken, chicken number 1, lays eggs. And the block next to it is the observation that this chicken, chicken number 2, lays eggs. And the next block over is the observation that this chicken, chicken number 3, lays eggs. And the fourth block over is the observation that this chicken, chicken 4, lays eggs. And we do a bunch more observations. Then, at a certain point, we would feel comfortable now, let me just show you what I've done. This chicken lays eggs, this chicken lays eggs, this chicken lays eggs, this chicken lays eggs. Then, sorry. I build a broader block, and what does the broader block say? This broader block says, all chickens lay eggs. So it's a rule, or a law, or a generalization, based on all my individual observations. So I observe this chicken lays eggs, this chicken lays eggs, this chicken lays eggs, this chicken lays eggs, so all chickens lay eggs. Really simple, right? I keep looking, and I say, let's try ducks. Yeah. So explain to me why. So you say duck is yasa, right? Chicken is chi, right? Why isn't it cheese? That seems like a dumb question. If you speak English, that's a really good question. If you speak English, you're like, why don't they say cheese? They say yasa. So I'm not even going to ask about watches because I learned about that the hard way. So but we're going to look at ducks, okay? So I look at this duck and I'm like, oh, that duck lays eggs. Second duck lays eggs. Third duck lays eggs. Fourth duck lays eggs. And what do? I conclude all ducks lay eggs. Now I notice that all chickens lay eggs, and all ducks lay eggs. And maybe I then say all crows lay eggs. You must have crows in China, right? Blackbirds are kind of annoying. No. Other birds. I pick other birds and they lay eggs too. Right? Whatever birds are common in China that comes to mind. And then, what do? Then I say, I go up a level and I say, this block, and what's this block? Somebody tell me, what do you think this block's going to be? I heard it over here, yeah.
All the birds.
All the birds lay eggs, right? Yeah, you say, yeah. I think several of you said it, yeah. So all birds lay eggs. This is an example of how the covering law model works. Now not everybody, this is just my example, I sometimes call it the pyramid model. But that's my phrase. That's not a standard phrase. It's just that I find sometimes it helps students to understand. It looks to me kind of like a pyramid. The just remember, if you say to somebody, oh yeah, the pyramid building model of science, unless they were one of my students, they won't know what that means. But if you say covering law models, people will know what you mean. Like, oh yeah, the covering law model of science. And what's the basic idea? You have observations. You have observations. I'm sorry, I can write that very clearly. Observations, which are the basic blocks on the bottom. They're kind of like what Russell meant by, I'm not going to say that. They're a little like sense data. Even that, I'm not sure I want to say that. But they're at the bottom are observations. Then as you go up, you get theory. And what's the theory? The theories are laws or generalizations. So all these chickens lay eggs, so all chickens lay eggs. All these ducks lay eggs, so all ducks lay eggs. All chickens lay eggs, and all ducks lay eggs, so all birds lay eggs. And these are the theories based on the observation. Now the basic idea, or one of the basic ideas of the covering law model is, because it's a pyramid, the bottom blocks, the observations, are fixed. Once you have them, they don't change. And the higher level blocks really don't change either. You just build the pyramid bigger and bigger and bigger. You get more and more observations, and then you put more and more big blocks on top to cover the observations. And so science just gets bigger and bigger and taller, and it's wonderful, like the Great Pyramids in Egypt. Talk about why that's probably wrong after the break. We'll take a quick break, 5 minutes. We'll show you each other. So the example in chapter 6 of the Structure of Scientific Revolution, which is one of the things I had you read for today, the examples in chapter 6, a large part of what they're designed to do is to show that this model cannot be correct. And we'll talk about those examples in a few minutes, and you'll see why Kuhn at least believes that they show this model has to be incorrect. But first, a little bit more background. So the covering law model, it's one of several models of how science works that are widely accepted and were widely accepted before Kuhn. And even today, some smart people do believe in the covering law model of science. But now I want to talk a little bit about the views that Kuhn developed in earlier chapters in the Structure of Scientific Revolution, leading up to chapter 6. One of the things Kuhn talks about, and this is his technical expression, is normal science. Normal science. What does normal science mean? Well, as the name suggests, normal science is just the science that scientists are doing most of the time when they're acting like regular scientists. But what is distinctive of it, Kuhn says, well, normal science is governed by a paradigm. Now, what is a paradigm? Kuhn admitted later in his career that he was not as clear about what a paradigm is in the body of the book as he should be. So Kuhn said later, the postscript, which we'll read part of, to the Structure of Scientific Revolutions, was written about a decade, I think, maybe 2 decades actually, after the original book. And in the postscript, Kuhn said, one of the things he said was that I should have been more clear in the book about what a paradigm is. And he said, I primarily meant 2 things by a paradigm. I meant a worldview. A worldview. What is a worldview? The worldview is what a particular conception of science thinks the world is made up of. What kind of things does this science believe in? For example, in part of the worldview, and hence part of the paradigm of Aristotelian biology, is God and final causes. Final cause is a technical term in Aristotle's thought. It just refers to a final cause is a way of explaining something in terms of the purpose it serves. So, in the case of human beings and things that human beings build, we still believe in final causes. So if you ask, what is the final cause of this cell phone? The final cause is to make money for Samsung. That's a joke. The actual final cause would be something like to allow people to talk to each other, to allow people to play games. In other words, what's the purpose humans make cell phones for? Now, actually, in fairness, Samsung, the company that made this, their final cause was to make money. But my final cause in using it is to talk to people on the phone, to play games. That's my dictionaries on here, all kinds of things. But for Aristotle, in biology, there are also final causes. So if you're trying to explain why the species developed the way they did, it's always going to have to be in terms of some purpose that they serve. So, for example, Why do humans have 10 fingers and 10 toes? Or why do men have nipples? Now, an Aristotelian has to explain these things in terms of some purpose they serve. There must be a purpose that's served by having 10 toes as well as 10 fingers. The 10 fingers, okay, that's not too hard. It's good for grabbing things. Why 10 toes? I might be out of date now, so the biologists in the group can correct me. But what I heard was, according to modern biology, we have 10 toes because it's just easier to encode that genetically than to encode 10 fingers and 8 toes. Maybe that's wrong. Maybe there's another reason in modern biology. The point is, for Aristotle, there has to be a reason why you need 10 toes. It can't just be some accident. There has to be a good reason. And there has to be a reason why men have nipples. They have to serve some purpose. And the purpose is determined by God. That's part of the paradigm of Aristotelian biology. In Darwinian biology, you don't have to deny God, but Darwinian biology doesn't appeal to God. So Darwinian biology doesn't say there is no God, but it says that's not how you do biology. You don't appeal to God to do biology. And you don't appeal to final causes. So whatever reason men have nipples, it's not because, it's not going to be because, God had some good reason for putting them there. It's got to be something to do with evolutionary forces. So those are examples of different worlds. And you can use examples from physics and things like that. Kuhn says, also in the postscript on page 175, he said the other sense of paradigm that I meant was an example of what good science is like. So an example of here's how you do science. Here's how you do it. Here's an experiment that we thought that was a good experiment. Or here's a book that we said, wow, that was a good book of science. So Kuhn says what he means by a paradigm is two things. He says it's agreement about a worldview. What is the universe basically like? What kinds of things are in it? God? Or do we not need God? Are there final causes or not final causes? Is there, are matter and energy two separate things? Or is there one thing, mass energy? Are space and time two separate things? Or is there space-time? Are there particles and waves? Or are particles just spiky waves? What kind of things are in the world? And the other sense of paradigm is an example of how you do science. So Kuhn says normal science is science governed by a paradigm. So in normal science, in most of the time in science, scientists agree about the paradigm. They agree about what the world is like, and they agree about what it looks like to do write a good scientific book. Within that paradigm, there can be a lot of disagreement. But they have to accept the paradigm to do normal science. But then what happens, Kuhn says, is eventually you get anomalies. And anomalies are things that don't fit the paradigm. They're things that a paradigm has trouble explaining. And Kuhn says when you first encounter an anomaly, you don't just give up the theory. Let me give you a nice example to illustrate this. I hope this example makes sense for you. This is a true story. This is actually 100% true. There's a very famous, you may have heard of it. There's a famous university in the United States, MIT, the Massachusetts Institute of Technology. Now since Newton, we've known that acceleration due to gravity, at least near the surface of the Earth, is 9.8 meters per second squared. So, in other words, if you drop something, it's going to fall at 9.8 meters per second, and its speed will increase by 9.8 meters per second every second until air resistance makes it reach a terminal velocity. But basically, if you were in a vacuum, say, and you were near the surface of the Earth, things accelerate at 9.8 meters per second squared. You don't need to understand the details of it, but just understand there's a well-established rule about how fast things fall. If you just understand that, you understand enough. There's a very well-established rule about how fast things fall. So the professors at MIT, true story, for years they were getting really mad at their students. Why were they getting mad at their students? Because year after year after year, the students at MIT were getting the wrong answer when they measured acceleration due to gravity. The intro-level physics classes, because I took a year of physics, in intro-level physics classes, one of the first experiments you do is you measure acceleration due to gravity. And they were getting the wrong answer year after year after year. They were always getting about 9.7 meters per second squared. And the faculty were getting really annoyed. They said, this is disgusting. You guys are the future of science in this country, and you can't even do a simple experiment that's basic to physics. What's wrong with you? And finally they said, we're going to show you students how to do it right. So the faculty got together and they said, let's do it and show them just how exact an answer we can get. So they did the experiments themselves. The faculty did the experiment themselves and got 9.8 meters per second squared. That's an anomaly. Now, why didn't we see headlines all over the world, from New York to Beijing to Wuhan to Jakarta, saying basic concept in physics overturned by scientists at MIT? Because they said, boy, that's weird. Well, we know it's not right. We know it's wrong. Why? Because acceleration due to gravity is 9.8 meters per second squared. We know that. This is an anomaly. It's got to be wrong. We have to figure out why it's wrong. Eventually, they decided, and if you know enough physics to be interested, I can tell you exactly what went wrong. But the short version of it is, the equipment they gave the students was fairly expensive equipment. But it turned out that if you used cheap, inexpensive equipment, it actually got a better answer than the expensive equipment they bought. The expensive equipment had a flaw in it, which biased the result and made it come out wrong. And so they went back to using cheap equipment that you could get anywhere. You could get the equipment they used at any store here in Wuhan, any supermarket, you get the equipment they now use. This is a really basic experiment you can do yourself. So, and so they said, oh, well, that's why we gave the wrong answer. Now notice, they got an anomaly. And so students, year after year, are getting this answer, and they don't say, ooh, we got to give up Newtonian physics. They say, well, no, we're not giving up the paradigm just because a few students, well, hundreds of students over years, are getting the wrong answer. And then they perform the experiment themselves, and they don't say, oh, we're going to give up the paradigm because we're scientists, and we got the wrong answer. They say, no, this is a really good paradigm. We're not giving it up. And they found an explanation. Now, I still believe acceleration due to gravity is 9.8 meters per second squared, but the reason I'm telling you the story is to see it's not necessarily irrational or wrong to hold out when an anomaly occurs. When an anomaly comes up, the rational thing is very often to say, well, I don't know how to explain this yet, but I know there has to be an explanation under the paradigm. The paradigm works so well, I just have to keep looking for the explanation. An anomaly only becomes a problem when it keeps appearing and all the best efforts of the theory to explain the anomaly either fail or develop worse problems. So when you try to solve the problem, you get a worse problem. And you try to solve that problem, you get a worse problem. Then you have a problem. And what happens when you have that kind of problem? You have anomalies that are like that, where you keep trying to modify the theory. And then eventually, you get revolution. You get a scientific revolution. What happens in a scientific revolution is because of the anomalies, people start to give up on the paradigm. And then a genius comes along, usually several geniuses, because usually you need more than one. Usually several geniuses come along and they come up with a new paradigm. And the new paradigm can deal with the anomalies. Now, so far, what Kuhn said is really interesting. I hope you agree. But so far, you might read all this and say, yeah, but why can't I account for all of that with the covering law model? Maybe all you're saying is, oh look, I found a duck that doesn't lay eggs. So, big deal, all these ducks still lay eggs. And I guess I was just a little too quick to put this block in place, but I'm sure I can find another block that covers all these ducks. I'll just trim this block a little bit here, big deal. And I'll put another block over here, and not a big adjustment. And the blocks are all going to stay basically the same. Why can't I just do that? Well, that's what Kuhn's talking to us about in chapter 6. He's going to say, once you understand these concepts, and then once you understand the examples he's going to give you, you'll see this model, the covering law model, won't work. Why? Well, let's see. Which example do you start with? Let's do the oxygen one. I had you write about the oxygen one. At the next break, if you haven't already put your assignment for today up there, put it up there. But you can wait until the break if you haven't done it yet. But just remember before, at the end of the next break, leave today's assignment up here if you will. So let's talk about the oxygen example, which I had you write about. So, Priestley performs these experiments, and he says, you know what, I've discovered something really interesting. I've discovered something that's really kind of fascinating. And what is it? I've isolated this new kind of gas in this bottle. And what does he think this new kind of gas is? Right? What does Kuhn think that this gas is? Anybody know? What's the gas in the bottle? According to, if I say Kuhn, I meant Priestley, I'm sorry. What does Priestley think the gas he's isolated in the bottle is? Dephlogisticated air. Very good. Right. And that's a fun word, super rare in English. I like to use it just because it's such a weird word. Dephlogisticated, the D means removed or lessened. So dephlogisticated means it had the phlogiston either removed or lowered. What's the phlogiston? So what's phlogiston? Phlogiston is a substance that's given out when?
Just burn.
Oh, burn, yeah, combustion. Yeah, I'm sorry, yeah, you were saying exactly right. I was just mishearing, yes. So, right, so when something burns, yeah, or there's combustion. No, you said it right. I just misheard you. I'm sorry. When something burns or there's combustion, like a fire. The theory, which not just Priestley, but many chemists in his era held, was when something burns, what is burning? Because that's a basic chemical reaction. And the theory people held was, well, when something burns, it gives off phlogiston. Right? It's this matter that things give off. And that's what accounts for the changes that things go through when they burn. When you burn them, they're giving off phlogiston. That's why they change, because they're losing some of their matter in the form of phlogiston. So what Priestley said was, well, this is interesting. What I managed to isolate here is dephlogisticated air. Or if that's too weird of a way to put it, you could just say, I managed to isolate air that has less phlogiston than regular air. This air is a lot lower than usual amount of phlogiston. Now, here's why it starts to be a problem about the covering law model. Because if we ask what is Priestley's theory about the gas, his theory about the gas is, well, it's dephlogisticated air. But we don't believe in phlogiston anymore. So now if you ask a chemist today, so tell me about phlogiston. I mean, if they're a really historically minded chemist, they might say, oh, well, that's something people used to believe in way back in the 18th century, but nobody believes in it now. But most chemists will just say, what are you talking about? Phlogiston, that's not a real thing. That's made up. So Priestley's theory about this substance is wrong. Now, if we talk about Priestley's observations, Priestley would describe his observations as things like, well, I took the dephlogisticated air and I performed this test on it and I got this result. But that observation is phrased in terms of the theory that we don't believe is true anymore. Then Lavoisier comes along, and Lavoisier says, yeah, I don't think this can be dephlogisticated air. And we think to ourselves, oh, right, well, Lavoisier, what an intelligent, forward-thinking person you are. Yeah, dephlogisticated air, that's stupid, that's absurd. What kind of idiot believes in dephlogisticated air? Good job, Lavoisier, for understanding that there's, this is not. So Priestley says it's dephlogisticated air, Lavoisier comes along and he says, no, that's nonsense. And so we think, oh, good, what a smart person Lavoisier is for understanding that the notion of dephlogisticated air does not make sense. And so what does Lavoisier says it is? He says that this isn't dephlogisticated air, it is a principle of acidity. That's an abbreviation for associated, ASSOC period, associated with caloric. What is caloric? Caloric is the matter of heat. Also not real. So we've got Priestley saying, this is dephlogisticated air. And we laugh and we say, oh, how absurd, how foolish people were like Priestley for thinking there was such a thing as dephlogisticated air. And Lavoisier comes along and says, yes, you're a fool, Priestley, you stupid Englishman. I'm from France, I know better than you. And so I know that that's not dephlogisticated air, that's a principle of acidity that's associated with caloric, the matter of heat. Well, that's not right either. Eventually, Lavoisier says, it's this whole different element, which we call oxygen. Then we say, okay, now you've got it. Now you've got it, Lavoisier. It's a different element, it's oxygen. Now, is the story over? I don't think so. Why not? So Priestley's theory is that what's in the bottle is dephlogisticated air. Is there such phlogiston being the substance that is released by things when they burn, when they undergo combustion, there's fire? Is there such a thing as phlogiston? No. Therefore, is there such a thing as dephlogisticated air? No. So the phrase, the theoretical term that Priestley uses refers to nothing. It's not preserved, it refers to nothing. Lavoisier, first theory is, he says, no, it's not dephlogisticated air, it's a principle of acidity. Is there such a thing as a principle of acidity? Well, there are acids, but that's not what he meant by this thing. He meant something different, a principle of acidity that combines with caloric, the matter of heat. So there's not a principle of acidity that combines with caloric either, so this refers to nothing. Then Lavoisier says, no, I was wrong, Priestley was wrong, it's a completely different element. It's oxygen. Now it refers to, but wait, when I was in grade school, I was taught, this is kind of misleading because I didn't actually invent this theory, right, unlike Priestley and Lavoisier, but I was taught this in grade school. In grade school, what was I taught? I was taught oxygen is an atom with 8 electrons orbiting around the nucleus. And the atoms go around the nucleus like the planets go around the sun. So the nucleus is this collection of protons and neutrons in the center. I still remember this little kind of diagram. I forget how many protons and neutrons there are in an oxygen atom. And then you've got 8, I'm not going to draw all 8 of them, little shells of electrons orbiting around in a nice little pattern like the planets around the sun. So I was taught that in grade school. Is that what Lavoisier means by calling oxygen an element? No, because he doesn't have the atomic theory yet. So when Lavoisier calls it by the name of oxygen, he's using our name, or the English name anyway, or actually, the Latin name. But what he means by it isn't an atom with 8 electrons orbiting around it. He has some different theory of what an element is. And that theory actually refers to nothing, because there's nothing like what Lavoisier understood an element to be. He didn't have our theory of atoms. Then you might say, well, the good news is Van Norden understands what oxygen is. Van Norden learned in grade school that oxygen is an atom with 8 electrons orbiting around a nucleus. So this is what an atom looks like. It's got these protons and neutrons in the nucleus, and then the electrons orbit around it like planets around the sun. Now, who knows their contemporary physics? Do electrons orbit around the nucleus like planets around the sun? No, they don't. Not according to contemporary physics. There is, and this sounds as weird in Chinese as English. It isn't your English, this is just weird. There's a probability cloud of electrons around the nucleus, and there's just a probability of there being an electron at a certain space around it. So it's more like a kind of probability mist of electrons. So when Van Norden in grade school learned that oxygen is an atom with 8 electrons, no, that's actually wrong too. So what Van Norden believed refers to nothing. This looks like a problem, because it looks like everybody was wrong about what oxygen was until contemporary physics got it right. Now, what do we say about this? Well, one thing you can say is, you can say, well, you're going too fast, Van. The theories change. But the basic blocks down here, right, they don't change. The blocks don't change no matter what else changes. But if we ask, what are these blocks? What are these blocks like? So let's consider a couple of views we might have about what an observation is like. scientific observation? What is one like? Well, here's a couple suggestions. Maybe you can see already why the first suggestion is not going to solve our problem. We might say, well, scientific observation is a report in the language of the theory of what we tested or what we observed. So, for example, Priestley could say, dephlogisticated air encourages combustion. Combustion is burning. So we might say, wow, it's a really interesting property of this dephlogisticated air that if I put something burning in there, it burns even brighter. And so the problem is this report is in the language of the theory. So when the theory changes, the observation will change, and you'll start losing bricks. In other words, if the equivalent of the sensory report, it's not like easy, like, oh, look, this chicken lays eggs. We're asking, what did Priestley observe? Priestley would explain what he observed by saying, well, I observed that dephlogisticated air supports combustion. But when the theory changes, that observation disappears. It's not constant. When we no longer believe in dephlogisticated air, the building block is now gone. What about if we say, well, it's not a report in the language of the theory, it's pure sense data, like Russell talked about. Now, this might work, right? Because sense data, as Russell uses them, the idea is you're supposed to know them directly. You're not supposed to be able to doubt them. They're somehow immediately present to you. But if we ask, does Priestley know the oxygen by means of direct acquaintance with the sense data? Yeah, you're shaking your head no. Why? You're right. It's okay. You're right. It's okay. That's all right. You're shy. It's okay. You're right, though. You're right to shake your head no. Right. Right. Why? Because if we ask, remember what sense data is for Russell. Sense data is only for Russell what you directly see, what you directly hear, what you directly smell, what you directly taste. There's no theory in sense data. So all Priestley knows about the oxygen in terms of sense data is, yeah, it smells like air. You ever smelled oxygen? I have. Guess what it smells like? Air. You ever looked at oxygen? I have. Looks like air. You ever tasted oxygen? I don't know if you can taste it or not. I guess you could. You can taste air. So I guess you can taste oxygen. It tastes like air. Right? So what does it sound like? If you put oxygen in a balloon, it sounds like a balloon emptying. Right? So it sounds like air emptying. So the sense data doesn't give you enough to distinguish the oxygen from anything like regular air. Because oxygen looks like regular air. It smells like regular air. You distinguish oxygen from air by its theoretical qualities. Like, well, it's an electron. It's an atom with 8 electrons around it. Or it's dephlogisticated air. So the idea is, if the problem with the covering law model, 2 problems. The theories aren't constant. So the top parts of the pyramid seem to change a lot. Even in between Lavoisier and us, it's tempting to say, well, look, maybe Priestley had it wrong and Lavoisier had it wrong when he called it a principle of acidity. But once Lavoisier started calling it oxygen, he understood what it was. But what Lavoisier meant when he called it oxygen was not what we mean by an element. For us, being an element is connected with being a certain kind of atom. An atom is connected with a bunch of other properties, none of which Lavoisier knew about. So the upper bricks always change. And then if you say, well, but surely the observations are constant. If you mean by the observation only sense data, well, maybe the sense data don't change. Although Kuhn's going to question that too. But even if the sense data were fixed, they're not enough to give you the scientific theory. You need more than that to distinguish oxygen from regular air. You need more than that to distinguish a planet from the sun. You need more than that to distinguish a comet from a star. You need theoretical terms. So the sense data is too limited to do that. So part of the point of the example of Priestley is to call into question the notion that there's either a fixed observation or a fixed theory that will let the current law model work. Let me say something really quickly about an X-ray example. So Wilhelm Röntgen discovered X-rays at the end of the 19th century. And really quickly, part of what's so important about the example of Röntgen is Röntgen discovered X-rays using a thing called a cathode ray tube. And the cathode ray tubes were the basis of the kind of television sets that I grew up on. The old television sets with the really big backs, and they've got these huge tubes in the back of them. So, and a cathode ray tube, you have a tube which various forms, but you have two positive and negative poles of electrical voltage in a vacuum sealed chamber. So it's a vacuum, there's no air in here. You have positive and negative voltage. And usually you'll also have something phosphorescent here. Because what will happen is you'll get a stream of electrons generated by this and will come out of the tube. And so once people discovered cathode ray tubes, they started doing all these experiments with them because they were really interesting. They're just all these interesting properties. They wanted to see, well, what do the electrons do? How do they function? What can I do with electrons? What effects do they have? And then Wilhelm Röntgen comes along. And Röntgen notices when he's doing something with a cathode ray, he's got the cathode ray shielded, but still there's a screen on the other side of his lab that is lighting up. And he's saying, why is that screen lighting up? I shielded the electrons in the cathode ray tube. It's not that. What's going on? So he spent 3 months of frantic research in his laboratory trying to figure out what's going on. And he eventually figured out that cathode ray tubes not only emit these electrons, they also emit this other kind of ray, which he called an X-ray, to reflect the fact that he didn't know what the heck it was. The X is just there to indicate, I don't know what this is. But he figured out that these X-rays have really interesting properties. So, for example, and you can look this up on the web, there's copies of it. The original still exists, and there's pictures of it. Röntgen took an X-ray of his wife's hand. And so he shot X-rays through his wife's hand because he noticed that X-rays could fog up a photographic plate without regular light. And so he X-rayed his wife's hand, and that's the first X-ray of a human body that was ever done, was Röntgen's wife's hand. And she said, I've seen my own death. Because she could see her own skeleton through the X-ray. But people were amazed by this. Now, why is this so important? Why is Kuhn focusing on this? It's a cool story, but why is it so important? What's so important about it is, it really bothered scientists. I mean, they were excited, but they were bothered. Why? They realized we've been doing all these experiments, but we haven't been controlling for the presence of X-rays. We don't know what results we've gotten that are because of the electrons and which are because of the X-rays. We're going to have to redo all the experiments we've done to check for the presence of X-rays. Why is that significant for the covering law model? Because now, all these observations, a bunch of observations are now gone. They're no longer scientific observations. They were made in controlled laboratory circumstances. They were taken to be reliable observations, but now they say they're not reliable observations. Throw them out. They're worthless. We didn't control for the possibility of X-rays also being generated by the cathode ray tube. According to the covering law model, though, observations are fixed. They're constant. We don't get rid of them. But Kuhn says, yes, we do. Here's an example of how we do. Things that were observations are now no longer. Okay, let's take a quick 5-minute break, and then we'll come back. is a problem for the covering law model because it starts to teach us that the theories change as we go over time, and not just the theories. It's hard to know how to isolate the description of the observation from the actual. So if I'm talking about the observations, it seems like normally scientists phrase their observations in terms of the theory, so we can't separate them. If we try to separate them, it's difficult because, for example, if we use Russell's sense data are very, very, very limited. And it's hard to know how to get from something like this smells a certain way, it has a certain color, it feels a certain way on my fingers, to this is oxygen, without a lot of theory in between those two. But if there's a lot of theory, then as the theory changes, you're not building something bigger and bigger, you're changing the structure as the paradigm changes. In the case of X-rays, part of what's interesting is that although the X-ray isn't opposed to the current, it was not opposed to the current paradigm, it was just a new kind of ray, still it undermined all these previous observations that before were fixed. People said, we tested such and such. We know what you observe if you do this. Now they have to go back and redo them because they said, we don't know when we got this effect. Were we getting this effect because of the electrons, or were we getting it because of the X-rays? We didn't know before there were X-rays, so we didn't know that we had to worry about them. But now we do. So old experiments, old observations, you get rid of them. So the X-ray example is a problem for the notion that somehow the observations are fixed and don't change over time. Finally, the Leyden jar. Unfortunately, well, the first part is not unfortunate. I actually own a Leyden jar. I bought one on eBay. And I thought about bringing it here to China, but it's fragile. And it's just packing it, I thought it's going to be so hard to pack. And I only use it for this lecture. This is the only time I use it in the whole semester is I hold it up and I say, this is a Leyden jar. You know, because it's neat to look at. And so what's a Leyden jar? Which Kuhn talks about as his third major example in this chapter. So as the name suggests, Leyden is just a town in the Netherlands where I think they invented these there, or at least they became famous there. It's just a jar. It's got a stopper, which is some kind of insulating material like cork or rubber. It's got a metal bar going through the stopper. And then there's metal. It's a glass bottle, but there's metal on the outside. So you've got a metal wrapper, you've got a glass bottle, you've got a non-conducting, in other words, a stopper that is cork or rubber, which are non-conducting. That means they do not conduct electricity. Electricity will not go through the stopper. It'll go through this bar. The bar is metal. So the electricity will go through the bar. And in the earliest version of the Leyden jar, they filled it with water. Now, what was the point of a Leyden jar? The point of a Leyden jar was people knew there was this thing, electricity. They thought electricity was probably a fluid. It was some kind of liquid. So electricity flows through things, so maybe electricity is some kind of fluid that we can capture. And so they said, well, if this electricity is a fluid, you should be able to put it in a jar, right? Most fluids, like wine, water, you can put it in a jar. So let's capture electricity fluid in a jar. So they said, well, how will we capture it in a jar? Well, we know that electricity likes to flow through water. We know it likes to flow through metal. So they tried various things, and eventually they settled on this thing, which is glass bottle, because why not glass? Because, hey, catch fluid, you put it in a bottle, right? And then they said, well, let's put some metal around the outside, because, hey, electricity likes metal. And we'll put a metal rod through the top, because, again, electricity likes metal. And we'll put some water inside, too, because, fluids, it'll mix in with the water fluid, and we'll have electric water. And then they discovered you can use this thing, and it will, in fact, hold an electric charge. It stores electricity. So they captured the electric fluid. There is no electric fluid. What is this? This is what we would now call either a capacitor or a condenser. A capacitor or a condenser is basically a conducting material, a non-conducting material, and then another conducting material. Again, conducting means electricity will go through it. It will conduct electricity. It turns out if you have like a metal and glass, say, and then another piece of conducting metal, you can store an electric charge in this. Just a basic fact about physics. It's a capacitor or a condenser. You can store a charge in it. It actually has practical uses. They used to use them in flashes for cameras. I don't know whether they still use them, but like electric flashes for camera, it used to have a capacitor. You would charge the capacitor from the battery, and then when you flashed it, that was the capacitor discharging. So that's what this is, according to us. But for the people who used it, it was a bottle where you caught the fluid that was electricity. And after a while, they tried different things, and they said, well, what happens if we get rid of the water? And they said, it doesn't work anymore. And they said, well, what happens if we get rid of the water, but then we put a piece of metal around the inside? Now the charge stays. Like, well, that's really interesting. The middle, this piece of metal here is really there in case you want to discharge it. It connects to the inner metal or the inner water in case you want to discharge it. But the important thing is, first they had water in here, and then they said, well, let's try getting rid of the water. Maybe we can get pure electricity. They got nothing. So they said, that's weird. Let's try putting metal around the inside. It works again. Wow, that's really interesting. We're somehow storing electricity in here. It doesn't seem to be anything in there, but we're storing electricity. Eventually they realized, you know what? It doesn't have to be a bottle at all. All it really needs to be is conducting material, non-conducting material, and conducting material. And now they've got a capacitor. So the reason Kuhn thinks this is interesting is he's saying, notice that when people first started using a Leyden jar, what they thought they were doing is, this is a jar we use to store the fluid that is electricity. We store the fluid that is electricity in this, just like we store oil or water or wine. Gradually, we come to think they rethought it until eventually they arrived at the notion of a capacitor. But this is a very different notion from the bottle where you store the fluid that is electricity. We look back and say they invented the capacitor, but they understand what they're doing as a bottle that stores the fluid that is electricity. Again, the theory of what you're doing is very hard to separate from the scientific observation. Because their observation is, look, I captured the fluid of electricity in this bottle. That's the observation. The last example, I think, is the most interesting. It's not an example from the history of science, it's an example from experimental psychology. And let me give a little explanation for it. I never know how familiar people are with Western playing cards. And I'm not saying that because I'm in China. I'm saying that because I've had this experience in the US as well. So Kuhn's anomalous is just a fancy word for non-normal. And of course, remember, anomalies are what lead to scientific revolutions. Anomalous playing cards, I've had the experience in the US as well as some students who just aren't familiar with playing cards. One year, I kept trying to explain this example to one student again and again, he wasn't getting it. And I finally said, well, you played cards, right? And he said, no, my mom didn't let us play cards. She thought that was bad. And I'm like, oh, okay, you don't know what a card looks like. Okay, gotcha. So I'm going to explain really quickly what regular playing cards look like. This might be really obvious to you, or maybe it's obvious to everybody, but like I say, sometimes I have had students in the United States as well who just never seen a regular playing card. Playing cards, a deck of regular Western-style playing cards. There's good historical reason to believe that not these particular playing cards, but the whole notion of playing cards originated in China, just historically speaking. But these style of playing cards originated in the West. I actually play a lot of poker when I'm back in the United States, where it's legal. So I know a lot about playing cards and things. If you're ever curious, I can tell you about the history of playing cards and why there are those suits and things like that. So there are 4 suits of playing cards. The suits are diamonds, hearts, these are hard to draw, spades, and clubs. Spades and clubs are black. The spade is itself black, the club is itself black. And the diamonds and the hearts, the diamond is red and the heart is red. And in every suit, there's a bunch of cards. Most of them have a number on them, like you might have a 2 of diamonds or a 5 of hearts. There's also some what are called court cards, king, queen, and jack, but they didn't use those in this experiment. So you might have, like, say, a deuce, a 2 of diamonds, a 5 of hearts, an 8 spades, a 9 of clubs, or you could have a 5 of clubs, or you could have an 8 of diamonds. You know, for every suit, there's all the numbers from ace, which is 1, up to 10. So, plus the court cards. So 4 different suits, and diamonds and hearts are red, spades and clubs are black. So in this really interesting experiment, they did this. They would get people who were familiar with playing cards, and they would flash the cards really quickly, maybe a second or a fraction of a second, and they would ask the subject to identify the card. And generally, people who are familiar with cards, we can identify cards very quickly. We can say, oh, that's a 5 of hearts. Oh, that's a 3 of clubs. Oh, that's a deuce of spades. Oh, that's the ace of diamonds, really quickly. Then they started to sneak in there anomalous playing cards. How were the cards anomalous? The diamonds and hearts were black, and the spades and clubs were red. If you are used to regular playing cards, that is positively disturbing to look at. Indeed, one of the scientists who did the experiment said it kind of hurt his eyes to look at the cards. It made him feel so weird. But then they would sneak them in. And just, so for a while it's just, 5 of hearts, 2 of spades, whatever. And then they sneak in like a black deuce, a 2 of diamonds, or a red 8 of spades. And the people are like, that's an 8 of spade. I think it was a heart, 5 of hearts. And then they get confused again and again and again. And then gradually they would increase the duration of exposure until the subjects would go, oh, I see what you did. And then they go back to 5 of hearts, deuce of diamonds, 8 of clubs, 3 of spades. No problem at all identifying. Pow, 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 pow. Really interesting result, right? Their expectation is this diamonds and hearts are red, spades and clubs are black. As long as their expectation was met, they had no problem identifying what they saw. When their expectation was violated, they didn't know what to say. Sometimes they would just misidentify. They just say, oh, 5 of hearts, when it's really a spade. Or, oh, deuce of clubs, when it's really a diamond. But a lot of times they would just say, that's weird, I don't know what that is. But then once they knew what they were looking for, super easy, no problem. They could identify them just as quickly as before. Interestingly, the experimenter said a certain percentage of subjects could never learn to identify the cards. Even if shown the new cards for several seconds. They would show them the varied cards, not tell them what was different, but just show them the black diamond or heart or the red spade or clubs for like 2-3 seconds. What is this? They'd say, I don't know. I don't know what that is. Like, what about this? I don't know. I don't know what that is either. So Kuhn says this doesn't prove anything. It's just one experiment. But he says it's very suggestive. Suggestive of what? You see what you expect to see. You not see, or you have a lot of trouble seeing what you do not expect. But once you have learned to see something in a new way, it becomes easy to see it that way. And you see it that way immediately. It's the easiest thing in the world. I've been explaining Kuhn. Let me speak in my own voice for a second. Speak in my own voice is an idiom. It means I'm just speaking for myself for a second. As a historian, what I often find is this. One of the reasons I like this first quotation technique so much. When I teach philosophers, especially in the U.S., I often teach traditional Chinese philosophy. And once I learned to understand traditional Chinese philosophy, it made so much sense to me. But sometimes when I'm trying to explain it to philosophers who haven't learned the paradigm of traditional Chinese philosophy, it's really hard to explain to them what it means. Because to them, in their paradigm, it doesn't make any sense. Because they'll look at it and they'll say, but why would you say that? And I'm like, why would you not say that? That's the obvious thing to say in this situation. It's the most obvious thing in the world. I don't want to have to go into specific examples because it would take us off our topic too much. But in office hours sometime if you want to, I can do that. But this is a very wide applicability. The fact that people can easily see what they expect to see, they find it very hard to see what they do not expect to see, and if you learn a new paradigm, all of a sudden it's really easy to see. Now, in the time we have left, I want to say just a little bit about one of the chapters that we skipped over, chapter 7. Just really quickly, one of the things it talks about is the transition between the Aristotelian Ptolemaic astronomy, which was geocentric, and the Copernican astronomy, which was heliocentric. Now, geocentric, geo means earth, like in geology or geography. So the geocentric, centric like central, means that in the Aristotelian astronomy, the Earth is the center of the solar system. In Copernican astronomy, it's heliocentric. Helios is the Greek word for sun, and centric again means center. In the Copernican view, the sun is the center of the solar system, and the Earth and the other planets go around it. Now, this is the transition from the Aristotelian Ptolemaic astronomy to the Copernican and then Galilean astronomy. It's one of the major scientific revolutions in the West. And I say Aristotelian hypo Ptolemaic, the P is silent. In the original Greek it was not, it would have been Ptolemy, but in English we don't say that. We just say, and Aristotle developed the basic view in the ancient world, the geocentric view, the view that the Earth is the center of the solar system and the sun and the planets go around it. But then this other astronomer, Ptolemy developed a precise mathematical version of it that you can use actually determine where the stars should be, where the planets should be, things like that. Copernicus then proposed this alternative hypothesis that the sun was the center of the solar system. Now, interestingly, part of the paradigm of the Aristotelian Ptolemaic astronomy that was shared by the Copernican astronomy is the view that all celestial just means having to do with the stars and planets. So all your stars and all celestial motion, all motion that had to do with the stars and planets is either circular or composed out of circles. So, although they disagreed about whether the sun or the earth was the center of the solar system, the Aristotelian Ptolemaic astronomy and the Copernican astronomy agree that all celestial motion, all motion of stars and planets, is either circular or it's composed out of circles. What does composed out of circles mean? One of the weird things about planets is that they have this thing called retrograde motion. So if you're watching the path of a planet like Mars or Venus, if you're watching the path of a planet from Earth, they will move through the sky in a line. Then they will seem to slow down, stop, turn back, and then go back on their course. And this part where they seem to stop, go back, stop, and then go back is called retrograde motion. And early civilizations, as soon as they got really interested in the planets, they noticed this. It's hard not to notice if you carefully watch the planets. Now, if you think about it, if the planets are moving in circles, it's a little hard to explain retrograde motion. Why? Because you need some explanation for why whatever is making the planets move all of a sudden slows down, stops, goes back, and goes forward. Now, the planets have been moving for thousands and thousands and thousands of years. How could it be the case that, well, they move forever? It's just that every now and then they stop, go backwards a little bit, then they start going forwards again. It's not very plausible. So what Ptolemy figured out is he said, well, suppose this E is for Earth. The E is for Earth. Dicho. And suppose over here we've got Mars, and we're trying to explain why Mars appears to have retrograde motion, why Mars appears to go across the sky, stop, slow down, stop, go back, then go back in the retro direction. And Ptolemy figured out, well, if you've got a circle on a circle, could explain this. In other words, suppose Mars is moving around the Earth like this, but it's also, what Mars is really doing, and this is an M for Mars, Mars is also moving on a circle that's on the big circle. If you combine the motion on the little circle with the motion of the big circle, and you get the speeds of those two circles right, you will observe from the Earth retrograde motion. Because sometimes the Mars will be here, and as it starts to move here, it will appear to start moving backwards from the Earth. But then eventually it will get here, and it will seem to start moving back in the normal direction. And as long as these circles are the right sizes and the right speeds, you'll observe the right thing. Now, when you have a circle on top of a circle, circle on a circle, that's called an epicycle. An epicycle. Now, what was happening as we get close to the time of Copernicus is people were observing the stars really carefully, observing the planets really carefully. And because they observed them so carefully, they kept developing more and more careful models of how they moved. But the thing they noticed was, after a while, they didn't just need circles, and they didn't just need epicycles. They needed epicycles on top of epicycles. Then they needed epicycles on top of epicycles on top of epicycles on top. They had to keep adding epicycles to keep explaining the motion of the planets. Because as they observed them more and more carefully, they saw more and more slight deviations in their course. And so Copernicus came along and said, well, look, why don't we just throw out this whole complicated Aristotelian Ptolemaic system and get a simpler one where the sun is the center of the solar system. Now, why did people switch to the Copernican system? Because now, after all, we believe that the sun is the center of the solar system. Well, one answer is, for a long time, they didn't. Actually, for maybe 50 or 60 years, there were very few people who were in favor of the Copernican view. Why? Well, actually, they had a bunch of good reasons. One of them I've mentioned before. If Copernicus is right, if Copernicus is correct, right, this is Copernicus's view that the sun, S is for sun, Titan, and then the Earth, the E. In order to explain what we observe, the Earth, the E, has to be revolving around the sun, but it also has to be rotating on its axis. That means that right now you are zooming around the sun at thousands and thousands of miles an hour, and you're spinning around the center of the Earth at thousands of miles an hour. Does it feel like you're spinning around the axis of the Earth at thousands of miles an hour while zooming around the sun at thousands of miles an hour? No. So people said, well, Copernicus' theory is cute, it's clever, but it can't be right, because it can't explain why it doesn't feel like we're moving. There were also biblical objections, because in the book of Joshua, Joshua was fighting one of the enemies of the Israelites, and he said to God, if night comes, they will escape. And so God ordered the sun to stop in the sky, so the Israelites could destroy their enemies. So many contemporary people said, well, look, the Bible's pretty clear on this. The sun moves, God stopped it, but it normally moves, so therefore we know it moves. Now, nowadays for us, we say, well, that's not a legitimate argument in astronomy. But in the Aristotelian Ptolemaic paradigm, at least the version of it that people accepted in Europe at the time of Copernicus, part of the paradigm was the Bible is a reliable source of scientific and historical knowledge. That was part of the paradigm, it was part of the worldview. So that was a good argument, actually. And Copernicus didn't say, oh, I think the Bible's stupid. He said, well, no, you've got a point, but that must be a metaphor. So that's not a bad argument either, but he had to give that argument. He had to explain this problem. So a long time, people didn't accept it. Why did they accept it? You will hear people say again and again and again that the reason people accepted the Copernican view was that it was simpler than the Aristotelian Ptolemaic. Whereas the Aristotelian Ptolemaic view kept needing more and more and more epicycles, the Copernican view was simpler. The standard textbook explanation of why people eventually converted to the Copernican view is that it was a simpler theory. It was committed to fewer epicycles. If you hear that view, and you are tempted by it, I recommend this book. The Copernican Revolution, by this historian you might have heard of, named Thomas Kuhn. This was a book he wrote before he wrote The Structure of Scientific Revolutions, called The Copernican Revolution. It actually is a really fascinating book. It's a really fascinating book. So if you like The Structure of Scientific Revolutions a lot, you should read this too, because you'll love this. And Kuhn, again, trained as a physicist. He knows his math. Can't accuse him of not knowing his math. Said, you look carefully at the Copernican theory and the Ptolemaic theory. Guess what? The Copernican theory is not simpler than the Ptolemaic theory. They both require epicycles because they both are committed to the notion that all celestial motion is either circular or built out of circles. So they both require epicycles, and they require just as many epicycles. So again, you will hear lots of intelligent people say, well, that the reason people went for the Copernican view is that it was simpler and so more plausible. Kuhn says, look at the actual theories. That's false. They're equally complicated, and people knew that. So why did people start to shift towards the Copernican view? Kuhn says, and this is more controversial, the claim about the Copernican and Ptolemaic views being equally complicated, that's, historians agree with Kuhn on that. That's not controversial. But the next thing Kuhn says is controversial. Kuhn says, if you want to know why people switched to the Copernican, the answer is scientists thought, I don't know, the Ptolemaic view just doesn't seem like it's going to work. Let's just try this view. That's about what it was. They just felt as if the Ptolemaic theory didn't feel like, it was more like a feeling. The Ptolemaic theory didn't feel like it was going to work. It seemed to be just, they could answer the problems and it wasn't any more complicated than the Copernican view, but they just felt like it can't be right. So they tried the Copernican one. That should surprise you. Because what that means is one of the world's major scientific revolutions occurred because scientists just felt like the previous theory couldn't be right. That's controversial. But Kuhn says that seems to be all they were going on. Just a feel that Ptolemaic view doesn't feel right anymore. It felt right before, it doesn't feel right now. Later, they got more evidence for the Copernican view. But for a long time, there actually was no definitive, no absolute evidence in favor of the Copernican view. Almost out of time, really quickly before I forget about it, before I have time to say. Interestingly, the Catholic Church, which was dominant in Europe at the time that Galileo came along, was actually overall fairly sympathetic to both Copernicus's view, and then when Galileo defended it, they were actually pretty sympathetic. Until Galileo got some support from the Vatican, from the Pope, and he published a dialogue on discussing the various theories, the Ptolemaic view, Copernican view. And in the dialogue, he modeled one of the characters on the Pope, and he put all the stupid arguments in the mouth of that character. And then the church turned against him. So I'm not saying that's right. My personal opinion is the church should still have let Galileo express his views. That's my personal opinion. But historically what happened was Galileo personally offended the Pope. He went out of his way to personally offend the Pope in defending the Copernican view. And as a result, the Pope turned against him. So that was the basis of the church's rejection of Galileo's view, not a general narrow-mindedness about the possibility that he could be wrong. I think that's all we need to discuss for today. So remember what I said at the start of class about our class meetings in relationship to Guojingjie. And I'll see you next time. Again.